Hello everyone. In this short video we will look at the characteristic chemistry of elements in the D block. The chemistry of the D block is a huge topic, and so this is certainly not comprehensive. It is a flavour of some of the most common types of behaviour. So here's the table, and the D block includes all the elements in group 3 all the way through to group 12. That's 40 different elements. Some will be familiar to you, others less so. I should say that the elements in the first row of the D block are relatively abundant. But that abundance decreases as we go down each group. And by the time we get to the third row, many of these elements are really rather rare. These are elements like platinum and gold, which are consequently very valuable. The fourth row are all radioactive. Only the first element, actinium, is naturally occurring, and this in very small quantities. All of the rest are synthetic, meaning they are man-made, and they are highly unstable, so there's next to no chemical studies on any of these elements. All of the D block elements are metals, and since they are metals, and since they bridge between the S block and the P block, they are often known as the transition metals. Many modern definitions of a transition metal actually exclude some of the end members from this group. The problem with that approach is that we are left with some elements that don't fall into any other category. So I will not pay too much attention to these sort of semantic arguments. When I say a transition metal, I mean an element in the D block, even if that element's characteristic behaviour is more akin to something in the main group. A good way to explore the characteristic behaviour is to look at one small part of the chemistry in a bit of detail. So if we consider just one set of relatively simple, say, binary compounds. So when I say binary, I mean a compound that is made of just two elements. And to give us some continuity and comparability, let's make the other element fluorine again. The transition metals characteristically form what can be described as mostly ionic compounds, where the metal becomes positively charged. By contrast, halogens, of which fluorine is the first member, like to form negatively charged ions. So we can look across the first row of the D block, from scandium to zinc, and for these elements we can ask, which fluorides are known? Here they are. We notice that some elements, there is just one compound. For example, scandium, the only fluoride is scandium trifluoride, and for zinc, the only binary fluoride of zinc is zinc difluoride. But for other elements, there are many distinctly different compounds. Look at chromium. There's a chromium difluoride, a chromium trifluoride, chromium tetrafluoride, chromium pentafluoride. So here, the chromium ion seems to exist as +2, +3, +4, or a +5 cation. You should compare the pattern of stoichiometries of S block fluorides and P block fluorides and the D block fluorides. These behaviours are characteristic for each block. They are not specific to the fluorides. So this is normal for transition metals. One element can be found with different cationic charges. Another thing that is normal for transition metal compounds is that they are coloured. Well, mostly coloured. There are some exceptions. Scandium 3+, titanium 4+, vanadium 5+, copper 1+, and zinc 2+ are always colourless or white. Although the transition metal ions can exist with different charged cations, some cations are much more common than others. For example, titanium can be +2, +3, or +4, but there are many more compounds where it's +4 than the other possibilities. So, although what I'm about to say is a sweeping generalization, it's perhaps useful. How commonly we observe something is broadly related to the stability of that species. We tend to observe the more stable things. So what you can see from this graph is that for the first few elements, it is the highest possible cation charge that is most common, and this continues up to a point. But for the second half of the period, it is the +2 or +3 ion that is most commonly found. I should also say that where it looks like the cation charge is high, we see a lot of evidence that the bonding between atoms is not simply an ionic interaction. What do I mean? Well, for example, titanium tetrachloride is a colourless liquid at room temperature. It is clearly much better described as being molecular. However, the situation is not always clear. The characteristics of a compound do not always clearly place it as being either an ionic, lattice, or a discrete molecular species. It is quite common for materials to show some intermediate behaviour. Okay, so let's have a look at some typical compounds and species. In almost all compounds of transition metals, it is the case that the D block element is central and is surrounded by a number of other atoms. We could call these coordinating atoms, and whether the species surrounding the metal are atoms, molecules, neutral or ionic, we could call the whole coordinating group a ligand. Here's an example. If you dissolve a copper 2+ salt in water, the cations and the anions usually become separated, and the copper surrounds itself with 4 water molecules, and it does this in a very particular way, with the 4 oxygen atoms of the 4 molecules located on the corners of a square, where the copper ion is at the centre. As chemists, we use a number of different ways of depicting such a coordination complex. We can write down a chemical formula, and we use square brackets to denote what is coordinated to the metal atom. The formula tells you what's there, but not how the atoms are grouped or groups are arranged. We may also have a mental picture of how spherical atoms may be stuck together. This is perhaps the most realistic three-dimensional representation of the species, but it is not easy to draw, and usually it is not the clearest way to depict the local geometry. For that, we often use lines, wedges and dashes to represent a particular three-dimensional shape in 2 dimensions. A simple line indicates atoms that are next to each other and in the plane of the page. A wedge line can show an atom or group of atoms that are coming out of the page, while a dashed wedge means that the group at the end is behind the plane of the page. So here's another example. If you have a very concentrated chloride solution and you add a source of cobalt 2+, you can get a deep blue coordination complex in which the 4 chloride ions are coordinated to the central cobalt ion to give a complex with an overall 2- charge. Here, the chloride atom ions sit on the corners of a tetrahedron. Here's another. Tungsten hexafluoride has 6 fluorine atoms surrounding the tungsten, with the fluorine atoms on the vertices of an octahedron. This complex is overall electrically neutral, and like the other examples shown here, behaves as a molecular species. Next is an iron hexacyanide complex, which also has a local octahedral coordination geometry, with each iron atom bonded to the carbon atoms of the 6 cyanide ligands. While transition metal ions can show a range of coordination numbers, the number of ligands surrounding the metal, some options are more popular than others. In particular, 6 is by far the most common coordination number. And as well as being able to support a range of coordination numbers, transition metals can also be found in a variety of different local coordination geometries. That said, there are some arrangements of atoms that are much more common than others. For example, when a transition metal ion has 4 coordinating groups, it is either tetrahedrally coordinated to those ligands, or all 4 ligands are coplanar and form the corners of a square. 5-coordinate complexes can be trigonal bipyramidal, but more commonly they exhibit a square-based pyramidal structure. And as for the most common coordination number, 6 ligands, the structure around the central metal atom is almost always octahedral. Transition metals tend to form complexes with some coordinating species. Often these are ions, but they may be neutral ligands. In all cases, they tend to be elements from group 15, 16 and 17 from the P block. Now, I want to show you a typical reaction of a transition metal complex. One of the most common reactions is that of ligand exchange. So for example, if we start with a cobalt compound that has been dissolved in water, we would normally have the cobalt hexaaqua species with 6 water molecules coordinating the metal cation. Adding an excess of ammonia to the solution will displace the water, and we would end up with a structurally very similar complex, a cobalt hexaamine species, where 6 ammonia molecules now coordinate the metal in an octahedral geometry. So, while there are very, very many ligand exchange reactions just like this one, this simple reaction actually hides a considerable degree of complexity. Transformations in chemistry always happen one step at a time. In this case, we exchange one water molecule for one ammonia molecule, one at a time. So now let's think about how this might progress. Swap one water for ammonia and we have a new complex. Swap a second water molecule and we can choose if we want to exchange a water molecule that was originally opposite the site of the first exchange or one that was adjacent to it. This gives us 2 distinct structures with the same composition. These are isomers. The process goes on. You can swap a third water molecule for ammonia, and again there are 2 different isomers. And there are 2 more isomers for the coordination complex with 2 water molecules and 4 ammonia ligands. But you may notice there is some symmetry in this process. With just 1 water molecule and 5 ammonias, there is just one possible structure. And in the final exchange, we get our fully substituted coordination complex. Overall, in an excess of ammonia, the reaction proceeds in a very straightforward way to give a single product. However, if you add less ammonia, you will be in this more complicated regime, and all of these complexes are accessible and indeed known. Okay, the chemistry of the D block is a huge subject with thousands and thousands of compounds. And with so many elements and compounds, we find applications of transition metals almost everywhere. So this video has very briefly shown some of the typical behaviour of transition metal ions. There is much more to come on this topic later in this year and again in years 2 and 3. That's it for now. See you soon.